Hi, this is Rosella, and this is lesson 14.8 on differentiability. And differentiability is easier to understand if you look at it first from calculus. And in calculus, we learned that there were 5 models in which the function is not differentiable in 2D, of course, and 3 of them were because it was discontinuous, and 2 of the conditions were because it was continuous, but it was not differentiable. So what exactly is differentiability? So the definition of differentiability is literally its ability to be differentiated, or simply speaking, the fact that it has a derivative in all parts of the function. But if you look at it in 3D, like here, it gets a little more complicated. And I just want to explain the different terms first before I show you the equations. So the error function is the function between the difference between the estimate, which is the tangent plane approximation, and the actual function. And a physical representation of the error function is right here. As you can see in the bottom, that's the actual function. And if you look on top, that's the estimated value at that point. So as you can see, there's clearly a difference between the values that is estimated and the actual value. So now you're ready to look at some actual equations. So the first part of it is right here, and that is how you calculate differentiability in 3 space. And I know that looks complicated, so let me break it down into components. So this, which is the numerator, is the error I explained previously, which is the difference between the estimated value and the actual value. And the denominator, which is right here, as you recall, in the derivative, you can't really get the derivative of one point. There has to be some kind of difference between them, which is represented with h and k, as you see here and here. A plus h and b plus k represents the next point, and therefore you have to get the difference between the 2 points in which you're calculating the derivative for, also known as the instantaneous rate of change. And why does this equation stand? Well, the answer to that question is correlated to why does it have to equal 0. So to answer that question, I'm just going to do the derivative in terms of x, which means instead of h is equal to 0 and k is equal to 0, which is what we're tending towards, all I'm going to do is similar to partial derivatives, in which I take the difference. So instead of both h tending towards 0 and k tending towards 0, I'm pretending that y is staying constant, so I only do h is tending towards 0, and therefore the error is only accounting for if x changes, not if y changes. And the bottom would actually be different as well because k equals 0, so the bottom would just cancel out and it'll leave it with that. So I wanted to expand the error to show that it is actually the actual value minus the predicted value. As you recall up here, it states that the predicted value is literally a function of the tangent plane equation, and since k equals 0, there's no y component, so it's just the function value minus the slope of x. And if you simplify that, you'll actually see that this is the partial derivative for x minus m. And if you put m on the other side, this is what it'll end up with, which is exactly right, because the slope of x is supposed to be the partial derivative in terms of x. So now that you understand the equation, it's actually time to try an example. And we're going to figure out whether this function, which is the square root of x squared plus y squared, is differentiable at the origin, which is the point 0, 0. To prove that, I just want to see is whether or not the partial derivative in terms of x and y exist. So because this part isn't that important to understanding differentiability, I already did it. So this part is just saying that you're getting the derivative and then you're plugging the function in, and then after simplifying it, the end result is that the partial derivative in terms of x is plus or minus 1. And then you'll realize if you do it in terms of y, instead of h squared here, it'll just turn it into k squared, and then it'll end up with the same thing. So the derivative in terms of y is also plus or minus 1. So now that you know the derivatives in terms of x and y both exist, is the function really differentiable at that point? So to do that, I would need the limit equation that was stated above, and like the previous example, I'm just going to do it in terms of h tending towards 0, so the k here would cancel out, and as you can see, it's exactly like the equation I used right here. So I'm not going to explain the equation again. Instead, I'm going to plug in some values. So I'm just going to do the numerator first. So for the function, which is just what the function is, and this part would be the tangent plane approximation, and for this case, f of 0, 0 would be 0. So the value is 0, and these two stay unchanged because we're not going to find what m and n is. And actually, in this case, I want you to see the entire differentiable limit in its entirety, including both h tending towards 0 and k tending towards 0. And now that you've seen that, I'm going to set k equal to 0 so that we just find out what the limit is in terms of x. When you set k to 0, you'll get this equation once you simplify and you put some stuff into the x and y, and you'll realize that the limit only exists if m equals to 0 for the same reason as before. But if m equals to 0, like I said, then this would cancel out because m equals to 0, and this limit will equal to 1. But if a function is differentiable, the limit has to equal 0, and since it's not 0, we can conclude that f is not differentiable. Okay, last example. So we want to see if this piecewise function over here is differentiable. And let's start with trying to partially derive it in terms of x. And to add on to that, the only point we need to figure out is differentiable is the point 0, 0, because it is the point that they transition. So let's start with the partial derivative in terms of x first. So this is just the limit definition in terms of x. And to clarify, we're only going to see what the behavior is for the function xy over x squared plus y squared, because it is this function that determines what the values of z is around the point 0, 0, not including the point 0, 0, of course. So this is why we only care about the derivative in terms of xy over x squared plus y squared, because as you remember, the derivative isn't just at that one point. There's a certain difference. So we want to know what the derivative is as it approaches the point 0, 0. So when we plug this function into the general equation, this is what we get. And by the way, because I'm only doing the partial derivative in terms of x, I'm assuming that y stays 0 and that there's no change in y. So because y is 0, the numerator would be 0, but the denominator wouldn't be because there's still a change in x, which is represented with h squared and h. And if you simplify it out, you'll see that it would turn into that, and then it would be 0. And by the same notion, the partial derivative in terms of y, fy, would also be 0, because if you think about it, if x in this case becomes 0, it'll turn into the same thing, except instead of h, it would be the limit in terms of k, but it'll turn out to be 0 nonetheless. So now that we know that both the derivative in terms of x and the derivative in terms of y exist, we have to figure out if it's differentiable. And not so fast, let's not do the complicated limit equation yet. Let's figure out whether or not it's continuous first, because the condition for it being differentiable is that it has to be continuous, and let's see if it is. So to do that, we need to evaluate the function xy over x squared plus y squared again, and this time we want to see its end behavior as it approaches 0, 0 from both directions. So to do that, let's plug in some numbers. If we plug in a number that's ridiculously small, like this number, you'll notice that I deliberately didn't make x and y the same, but regardless, the number gets really, really close to 0.5, and that's to be expected because the difference between x and y as you approach 0 from both x and y gets really, really small until it technically just becomes about that. And that means it'll simplify to 1/2, which is, if you graph it, exactly what it approaches. However, 1/2 does not equal 0, which is the actual value at 0, 0, which means the function is not continuous. So that goes back actually to our Calc BC lesson, in that if it's not continuous, the function cannot be differentiable at that point. And of course, there's other conditions as well, such as if a function is differentiable at a point, then both derivative, and which is fx and fy, has to exist there. And also that having both partial derivative, as we saw in example 1, does not guarantee that the function is differentiable there. And I would also like to add the one in example 2, which is that it has to be continuous. Thank you for watching, and hope you learned something.